Okay, so far we have been able to discuss the Maxwell's equations for the empty space and for the media, and thereafter we had seen that these Maxwell's, the electric and magnetic fields, could be written in terms of the vector and scalar potentials, which by means of the gauge fixing conditions should be able to solvable for the phi and a as a function of the sources, which are the charge density and the current density. So once we have all those sorts of things, we should now be able to focus upon some interesting features of the Maxwell's equations and its applications. So as a simplest application, we will in this lecture we will study the plane electromagnetic wave in non-conducting media. So when we say non-conducting media, that means the sigma is 0, and we will also assume that there is no charge, as these are just the electromagnetic waves. Okay, so sigma is 0 is equal to rho. Okay, so with these sorts of setups, J, what is J? So this implies that the J is going to be also 0. So now with these sorts of things, we could write the Maxwell's equations. So these would be given by del dot E is 0, which is the first equation, del cross E plus 1 over C, del B by del T is 0. The third equation is going to be del B, that's also 0. And then the fourth equation is going to be del cross H minus 1 over C del D by del T, that should be equal to 0 as well. Now we could write this equation in terms of B and E as well. So this is also written as del cross B minus, so H is B by mu, so mu will go up, and similarly epsilon will come from here. So this is going to be epsilon mu by C del E by del T, that's 0. So this is my equation 1.1, equation 1.2, equation 1.3, and this is the equation number 1.4. So now we will proceed with these equations to find out the equation, the wave equation for the electric and the magnetic field. So let's start operating the curl of this equation 1.2. So taking curl of 1.2, what we will get? We will get del cross E, and that should be equal to 1 over C del T. As we know that we could write the derivative, either we could do the time derivative first or we could do the curl first. So this is going to be this. Now we know that this is going to be written as the divergence of gradient of E, which is del square E, and then the next term would be del square E. The second term is going to be gradient of the divergence of E plus 1 over C del over del T. Now what is the values of del cross E and del dot E? So, well, this is 0 as we already know, and del cross B according to this 1.4 is going to be epsilon mu by C del E by del T, and that is 0. So therefore from here we got a wave equation that looks like del to E minus 1 over C del 2t by del t2e is 0. And similarly, we could take, taking curl on 1.4, we get, let's see what we get. We will get gradient of curl of B minus epsilon mu by C curl of del T of curl of E. So this will give minus del to B plus gradient of divergence of B minus epsilon mu by C del T. Now we will put the values. Del dot B is 0 according to 1.3 and del cross E according to 1.2 is minus 1 over C del B by del T, and that should be 0. So therefore we get del to B minus epsilon mu and then by C square. We will have plus and now we are multiplying with this minus, so C square, and then we will get del 2B by del T2 is 0. Or we could write, together we write del 2 minus 1 over B square and E B, that should be equal to 0. This is my equation 2 with, I have defined B to be equal to C by epsilon mu square root. So this is my equation number 3. So the masses that this equation gives, so obviously the solution for this equation 2 will have solution of the form. So what would be the solution? E and B, they will be having the solution as E0, B0 and then e to the power I k dot r minus omega t. So that's going to be the solution for these equations. And obviously these are wave equations, no need to tell. So what are these k's and omegas? Well, k's and omegas are something like this. K is given as omega by b. So as you could say that, see that this is going to be the wave number. Okay. So now k is omega by b or omega by c, and just putting the value and epsilon mu. Or this could also be written as n square epsilon omega by c. So with n is defined as the square root epsilon mu, and this is known as the refractive index of the medium. Okay, K you already know is the wave number. Omega is the frequency, or rather the angular frequency, and c is the speed of light, v is the velocity of b. Okay, so with these sorts of things, now we could check something more, it's something very interesting. Number one is that we could write k dot r to be some direction says I. Okay, so then that means we could write, for example, this is what I mean, that this is my k vector and this was say my r vector. So now I am projecting basically the r vector on this. So this is basically the xi direction. So this is the projection of r on xi. So now with these sorts of simplifications, I'll put the values of E and B in terms of E naught and V naught into all these Maxwell's equations. Okay. So let me write this as equation number 4 using 4. 1.1 to 1.4 becomes. So now I will check what these equations become. So therefore I am not going to remove any of these things as we need to use them. What I will do, I will simply move from here onwards to show what's happening. So we have del dot is 0. Now remember, when del operates on e to the power ik dot r, or say rather ik xi, what we will get? No, I'm sorry, this is ik dot r minus omega t. So whenever we have a gradient operation, what we will get? We will basically get ik vector and then dot. This is gradient, so that means ik vector, and then I will get the same thing again. Similarly, when the time derivative operates, it will act upon the time part of this. So therefore, we are going to get minus I omega e to the power ik dot r minus omega t. So with these things, let's try to write down the del all these 4 Maxwell's equations in the simplified form. So del dot is 0. What does it mean? Del, that means k dot e. So that is del. So del dot e would simply mean that del has acted upon k. So this is going to be ik dot E naught. E naught. So basically what I'm doing now, let me just show you what I'm doing. So this is E naught, e to the power I k dot r minus omega t, that is 0, and that would mean I will get ik dot, and then this whole thing will come, that would be E naught e to the power I k dot r minus omega t is 0, or that would imply ik, or rather k dot e is 0. Okay. So similarly, so this is 2 point, I'm sorry, this is 5.1. And similarly, I will keep doing these things. So del dot b, for example. So 5.3 will give k dot b 0. Now from here, what we will get? Del cross e. So del cross e, this is 5.3, which will come from 1.3 del cross e, that is ik cross e, and minus I omega by c, and then b, that is 0. So therefore we conclude that the b is basically ck by omega. So this is ck by omega, and then cross e. Now ck by omega, well this is just the omega hat vector, so omega is ck, so basically we will survive with n hat direction. So b hat is n hat cross e. Now this is 5.2, this is 5.2. Now the final equation will be something like this. So final equation is del cross b, that would give me K vector cross B is B minus epsilon mu upon C del E by del T. So this is minus I omega and E. Or in other words, E vector is going to be minus C K by omega, and then we have 1 over epsilon mu, and then we have K vector here. I'm sorry, this is C, this is epsilon mu C K vector cross B. So this is going to be, so omega by C K, that's n hat, and then over, so here we have n hat, n vector, this is n hat direction rather, and then we have n square cross b hat, so that's 1 over n, and then we could write n hat cross b vector. Okay, so from here what we conclude, so this basically you could write also these things as the k hat direction. This is k hat direction. This could also be written as k hat direction upon n, k hat direction upon n, and then we could write this as b. So from here let's start concluding what we have, what is happened. So 5.1 implies E is perpendicular to K, and 5.2 implies B is perpendicular. So these alone implies that both E and B are also perpendicular. And also if we just check any of these equations, 5.3 etc., I'm sorry, this is 5.3, so this is 5.2, that says that B is perpendicular to E and K. So now let's picturize these things. So we have the x-axis, the y-axis, the z-axis. So now what we had happened, so this was the r direction. However, k dot r would be a z direction. This is where the r is, projection. And now basically this is what we have. This is how the waves are traveling. So they are traveling perpendicular to this direction, and we will have all the components. Okay, on one side we will have E, other side we will have B, etc. So another interesting thing that we might be able to note from this equation 5.2, 5.2 also implies that B by E magnitude is going to be 1 over simply n. This should be n. B is going to be n, in fact. So this should be n. So this could also be written as E naught, B naught by E naught as well. The other conclusion from here itself we could draw is that E naught by H naught. So that means we will be now dividing by mu again. So that's going to be, so n is, so that means we are dividing, n is what? So this is n upon, I'm sorry, this is 1 upon n, and then this is upon mu. So this is 1 over root epsilon mu upon mu. So that's going to be root mu upon epsilon. So this is called the wave impedance and referred as eta. So this is known as the wave impedance. We might be using these concepts little bit later. So thus we have been able to study the solutions to the plane electromagnetic wave, and therefore how it will propagate into the space has also been understood. In the next lecture, we will replace this non-conducting medium by the conducting media and will again rederive this whole thing to see how the directions or magnitude of the electromagnetic wave components changes while we have a non-zero value of the conductivity. Thanks.